All right, subscribers, welcome back to another episode of Science with Surbeck. Today we're going to look into section 13.2, which deals with forces of attraction. Now, before we get into the details of the notes, there are two objectives that I want you to be able to meet by the end of this lesson. The first objective is to describe and compare intramolecular forces and intermolecular forces. And objective number 2, you should be able to distinguish among intermolecular forces. So in section 1, we introduced the kinetic molecular theory and described the behavior of gases. Now, before we describe the other two states of matter, solids and liquids, I want to take this section and I want to talk about some of the forces that are at hand when molecules interact with other molecules or other particles interact with other particles. So we start here with the differences in these definitions. And our that's an RA, so intramolecular forces are the forces that exist within atoms. Again, the key word here is within. Now, the best way to describe intramolecular forces is through some examples. One example is ionic bonds. Another example is covalent bonds. And a third example is metallic bonds. Now, it should be noted that intramolecular, these types of forces are the strongest of all forces. These are greater than these intermolecular forces that we're getting ready to talk about. So now let's shift gears to intermolecular forces. Now, intermolecular forces are forces that exist between atoms, molecules, or ionic compounds. Now, these intermolecular forces hold more than one atoms, molecules, and compounds together. And as mentioned before, these intermolecular forces are weaker than the intramolecular forces. Now, there's three types of intermolecular forces that we're going to talk about in more detail. The first of which is a dispersion force. The other type of intermolecular force is a dipole force. And the third type of intermolecular force is a hydrogen bond. So let's go ahead and look into each of these three forces into a little bit more depth and detail. So we start out here with dispersion forces, and these are defined as weak forces that result from temporary shifts in the density of electrons in an atom's or molecule's electron clouds. Now, these dispersion forces can also be called London forces. And now, why are dispersion forces occurring? Well, we have this. Molecules are often or almost always in motion. And as they're in motion, they're going to collide into one another. And when these collisions occur, the electron cloud of one molecule repels the electron cloud of the other molecule. So, another thing to note here before we move into the details, when I talk about molecules, I'm referring to atoms or compounds here, so you could insert there. But atoms, they're going to be moving, and they're going to collide into one another, and it's going to cause these temporary shifts in their electron cloud. So if you can imagine for one moment here, let's say we have one electron cloud and another electron cloud, and they're moving towards one another. What happens here? They hit each other, and what happens, instead of having that perfect circular portion here, you're going to get this oblong shape just momentarily, and what you're going to have is a partial positive and a partial negative portion created on each of these areas. And what happens specifically here is that the repulsion that is experienced as these two things collide, what happens here is it causes the electron density around each nucleus of the atom to be greater in one region of each molecule. Again, creates these oval type of shapes. Now, this repulsion, what it does is it creates a temporary dipole, which is an area of partially positive or negatively charged region. Now, it's important to know that these dispersion forces occur between all particles. And they only become a significant force when there is no other forces of attraction between molecules. Now, to continue on with our discussion about dispersion forces, we get to this. Dispersion forces are the weakest intermolecular force because they are only temporary. And we also have to keep in mind that as the number of electrons involved in a molecule increase, the dispersion force between the molecules also increase. So a good example of this is the states of matter in halogen molecules. Fluorine and chlorine gas are they're gases because they have the least number of valence electrons. And then bromine is a liquid because they have more non-valence electrons than fluorine and chlorine, but less than that of iodine. And then iodine, I2, is a solid because it has the most number of non-valence electrons. Okay, so now that we've identified the properties associated with dispersion forces, we can move to our second of three forces that we need to talk about. So our second force that we need to talk about is the dipole force. And a dipole force is defined as attractions between oppositely charged regions of polar molecules. Now I underlined it, but I'm going to emphasize this again. These occur between two polar molecules. Now what we have to remember about polar molecules is that they contain permanent dipoles. And so remember, permanent dipoles are regions of the molecules that always contain a partial positive or a partial negative region. So an example of this is hydrochloric acid. So in hydrochloric acid here, we have to remember that we have an H that is bonded to Cl. Now, the Cl pulls those electrons closer to it. It has a higher electronegativity. And so this creates what we have as follows. So around our Cl, we get this fancy symbol that looks like an S that just stands for partial. And so we get a partial negative around the Cl. And because the electrons are pulled away from our hydrogen, this area here gets a partial positive. Now, this is permanent. They're always going to have a partial positive and partial negative poles to them, or regions, and so that's where we get that polar molecule. Now, we also have to remember that polar molecules orientate themselves so that oppositely charged regions line up with other polar molecules. So now let's say we have a bunch of hydrochloric acid molecules here, and we would have this occur. We would have our H and Cl, and remember the Cl has the partial negative charge and the H has a partial positive charge. So if we had many molecules, which is normally the case, normally you can't isolate one molecule by itself, but the Cl from another HCl would orientate itself towards the H. And so what would happen is you have this natural attraction between the oppositely charged regions here. Okay, so if we were to connect another molecule here, we would again have the Cl line up with the H, and that is because these partial negative charges would be attracted to the partial positive charges of the hydrogen. Now, what you often see here with dipole-dipole forces, and sometimes you'll see this on pictures or figures here, is that they will form this kind of attraction here, and they show that by some dots in between each of those molecules. So just as a reminder here, the partial positive hydrogen atom in one molecule is attracted to the partial negative charge in that chlorine atom. So again, there's that stated here. The partial positive of one hydrogen atom is attracted to the other partial negative charge of a chlorine in another molecule. Okay, so now we can shift gears and we can talk about our final intermolecular force. And that final intermolecular force is a hydrogen bond. Okay, so a hydrogen bond is defined as a dipole-dipole attraction that occurs between molecules containing a hydrogen atom bonded to a small, highly electronegative atom with at least one lone pair of electrons. Now, to be classified as a hydrogen bond, it's going to require the atom hydrogen bonded to one of the following atoms. One, it can be bonded to a fluorine atom. Two, it can be bonded to an oxygen atom. Or three, it can be bonded to a nitrogen atom. Now, the reason that the fluorine, oxygen, and nitrogen atom are used or have to be required in a hydrogen bond is because they are electronegative enough to cause a large partial positive charge on the hydrogen atom, yet they're small enough that their lone pair of electrons can come close to those hydrogen atoms. Okay, so another thing too, I'm just going to verbally say this, is that hydrogen bonds, yes, they have the name bonds in their name, but they're not like a covalent or an ionic bond where there isn't a sharing or giving electrons. This is just a really strong, again, you can think of it as almost as a connection between each and every molecule that contain these certain criteria. So these are still an intermolecular force even though there's bonds in their name. Okay, so I want to do one more thing that kind of ties everything that we've talked about in terms of intermolecular forces all together. And that is a little bit of an application here. And so we go through here and we want to talk more and more about hydrogen bonding. And so we look at three different molecules. We look at H2O, we look at methane, which has the formula CH4, and we look at ammonia, which has the formula NH3. And I tell you this, water is a liquid at room temperature, whereas methane and ammonia are gases at room temperature. And so what I want us to do through what we have just learned is I want us to determine why are methane and ammonia gases at room temperature, but water is a liquid. Well, let's first start with H2O. Let's first start with our water. Well, we want to list out this. We want to list out the types of forces involved in H2O. So the intermolecular forces that we just learned about, we said everybody has a dispersion force. So H2O is going to have a dispersion force. It's also going to have a dipole-dipole force, and that is because H2O is a polar molecule here. If I draw it, and we looked at an electronegativity chart, we would get our partial positive around our hydrogens here, and we would get our partial negative around our O4 oxygen. So it is, by this definition here, having a dipole-dipole force. And then check this out. Remember, to be a hydrogen bond, you had to have a hydrogen bonded to one of those three molecules, which would be fluorine, oxygen, or nitrogen. Well, hey, H and an O constitute our hydrogen bonding. So H2O also has hydrogen bonding. So the intermolecular forces in water are very, very strong. If we want to note this here, the intermolecular forces in H2O are very strong. And so that is why water is a liquid. But now let's explain why CH4 and NH3 are not liquids. Why are they gases? So let's start out here with CH4. Why is CH4 a gas? And the reason that CH4 is a gas is that it does not contain a bond between a hydrogen atom and one of those molecules of fluorine, oxygen, or nitrogen, and it's also nonpolar. So because CH4 does not contain a hydrogen bond and is nonpolar, we have very, very weak forces. And so the only intermolecular forces playing on our methane molecules, if they're all together, is the dispersion force. And so, okay, that explains why methane is a gas. It only has dispersion forces, which are the weakest. But now we need to get to nitrogen, NH3 ammonia. And this is kind of an unique case here. Well, let's remember that nitrogen or ammonia is going to contain an H with one of these FON molecules. So NH3 is going to have hydrogen bonding. And if I haven't mentioned already, hydrogen bonds are the strongest intermolecular force here. Okay, so if ammonia contains the strongest intermolecular force, why is it not a liquid? Well, the answer to this comes from something that we studied when we talked about the polarity of molecules, and that is this. Oxygen is more electronegative than nitrogen. What happens as a result, the oxygen-hydrogen bond in water is more polar than the nitrogen-hydrogen bond in ammonia. So it's pretty cool here with this question of why water is a liquid and methane and ammonia are gases. We put a lot of concepts of chemistry together with what we have just learned. Now, what I want to mention here shortly is the strengths of our intermolecular forces. So one, the strongest intermolecular force is a hydrogen bond. The next strongest is a dipole-dipole force. And then the weakest intermolecular force is a dispersion force. So those are some things to keep in mind as you rank these different types of intermolecular forces. All right, so this was a good lesson on intermolecular forces. It starts to tie some concepts of solids, liquids, and gases together. And it's something we can utilize really when we talk about solids, liquids, and gases from here on out. So this concludes this section of Science with Surback. I hope you have enjoyed this video. And as always, if you haven't subscribed, make sure you subscribe.